Hi everyone and welcome to Nanotalks. My name is Ryan Ramsey from DENSsolutions and today we have Marina with us, one of our new employees. Say hi Marina.
Yeah, hey everybody. Thanks, Ryan.
Well, so this is our second Nanotalks and we've invited our very own Marina onto the show. As I said, she's only just started with us and she's graduated and just finished her latest PhD and she's going to tell us all about it. So why don't you tell us a little bit about yourself?
Yeah, of course, I'll try. So at the moment, I'm a product marketing engineer in DENSsolutions, and I work closely with our customer and help them to give them tools to perform their experiments, let's say, faster, easier, and with more success. For 3 years, I was a PhD student in a technical university Darmstadt, where I was working on in situ TEM techniques such as in situ cold stage, hot stage, and electric field. Today I would like to show how powerful is the TEM technique for studying the main evolution in piezoceramics, actually. So these experiments have been performed in Technical University Darmstadt and in Ames laboratory in Iowa State University. Okay, let's get started. Well, I spent very great time in Darmstadt University, which locates in Germany in the area close to Frankfurt. Here you can see an image of our material science building where our TM facility locates. So here we have quite a few TMs, SEMs, and FIB. Yes, that's basically about my university. Okay, today I would like to talk about barium zirconium titanate, barium calcium titanate ferroelectrics. I will talk first of all I would like to tell you a bit about structure and phase diagram, then I will switch to materials and methods used for these experiments, and then I will tell you about TM results, and it will be in situ electric field investigations of this ferroelectric material. Then I will summarize everything.
Okay, well,
Yeah.
before we get into it, can you tell me a little bit about why these particular materials are important and I guess the application attached to that?
Yeah, sure. So in general, ferroelectrics plays really great and important role in our modern life. A large variety of applications such as piezoelectric actuators, sensors, some ultrasonic motors, capacitors, based on these materials. And let's say markets are growing and growing and growing. And basically, scientists who worked closely with this kind of materials know that lead-based materials with perovskite structure dominated on the market. However, due to toxicity of heavy metal lead, it's necessary to search for some substitute with comparable properties. And in the recent past, scientific interest was given to this composition because of very high piezoelectric properties. So that's why today I'm going to talk about that.
Great.
Okay?
Excellent.
Okay. Just a bit of literature review. So barium zirconium titanate, barium calcium titanate is a ferroelectric material with a perovskite structure, where barium atoms on the A side are substituted by calcium and titanium atoms on B sides are substituted by zirconium. So initially this material was synthesized by Leo and Ren, and they proposed such a phase diagram. And you can see that this system has three phases basically. It's pyroelectric cubic, ferroelectric rhombohedral, and ferroelectric tetragonal. So what is very important that it is the appearance of this morphotropic phase boundary in between of ferroelectric phases, where the properties peak actually. But a few years ago, Kibel proposed a different phase diagram where orthorhombic phase appeared in between rhombohedral and tetragonal. And the phase convergent region where actually four different phases coexist in very narrow temperature and compositional range. Okay, so as you already understood, this material was chosen for the studies. I will call it BZT-xBCT just to be shorter, and we was investigating different compositions. These compositions was chosen especially because it locates in different parts of phase diagram, so we choose rhombohedral, orthorhombic, and tetragonal material. All materials was synthesized using a solid state reaction method. Yeah, you can see all parameters on the slide. And in situ electric field investigations was performed in Philips CM30 and CM20 microscopes, basically.
Okay, and actually one thing that a lot of people often ask about is the sample preparation. So how was that for this TEM sample?
Okay, so in this case it was a standard sample preparation procedure, including grinding, polishing, dimpling, and final ion milling of the material.
Okay.
Which is quite commonly used. Okay, for our experiment, this Gatan double tilt holder was used. And what did we do? First of all, we sputtered gold electrodes on the flat surface of our sample. Then our sample was glued into the holder tip with an insulating varnish. And after that, electrical contacts of the holder was connected with copper or platinum wires to the spacement. So the distance between electrodes was 150 micrometers. Highest applied voltage was 500 volts, and electric field was perpendicular to the electron beam.
Okay, great. Well, everything about Nanotalks, we want to make sure it's about the technique and the methods that people are using. So can you go into a little bit about how, I guess, you used the holder, what kind of challenges that you were faced particularly, and I guess the solutions attached to that?
Yeah, okay. So, well, this holder works for this kind of experiments. That's why we use it, of course. But the main challenge of that is experimental difficulties. For instance, to glue this kind of wires, which are in our case, most of the time I was used platinum wires, which are 50 micrometers, and it's very difficult to glue it by hands to the sample, and to glue sample to the holder. And just to my experience, in my case, out of 10 experiments, successful was maybe half of that in the best case.
And how much time did it take you to, I guess, prep and that in each time then?
Okay, after sample preparation, it takes, let's say, 1 day to glue a sample and contacts, and basically next day you can do experiments. So after sample preparation, which can take up to 1 week, yeah, depends on how busy is equipment and so on, then you need only 1 day to glue everything to the holder tip, basically.
Okay.
That's it. Yeah, so also like another challenge just would like to mention, so in order to have a preferable orientation of our sample, of course we need a double tilt possibility. And in our case, first of all, I didn't expect it, but our double tilt range was reduced due to these wires, actually. Basically, you cannot tilt it on the high angle, because otherwise this wire will be unglued and you will lose the contact, and your experiment will not, you will need to stop experiment. So in better tilt was around plus minus 5 degree. I mean, well, which was quite fine for my kind of experiments. So what else? I just forgot to mention that the electric field in the TEM specimen is not uniform due to the presence of this central perforation. And basically the highest field we have in these darker areas of the sample where we perform all our experiments and where we take images and so on. And so the actual value of electric fields is not known, and it is basically calculated from the distance and the voltage, which you can see here. So also very important point, when you sputter gold electrodes, we use a special masks. So yeah, such kind of mask with certain distance, and also very important to have a certain thickness of your sample, that you will not get any shadowing of for the sputtering. So otherwise you can have as a more gold evaporated in the middle part, and then you will get an additional contrast during TM in the best case, or in worst case you will not be able to perform any experiments.
So did you have any solutions to overcome some of these challenges that you faced during your experimentations here?
Yes, for example, to increase a better tilt possibility. So what did we do? Firstly, we was using a copper wire, and the copper wire you can see in this image, which is around 230 micrometers. It was easier to glue, but of course better tilt range is reduced because it's, let's say, harder, and it will not allow you uh, to tilt in the higher angle. However, if you will use platinum wires for contacts, which are around 50 micrometers, you will increase this better tilt possibility. So this was one thing. Second of all, yeah, we got used to prepare certain thickness of the specimen. It's 180 micron in the edge, let's say, in order to put it to our masks. So we will not have any shadowing for during sputtering of gold electrodes, for example.
Okay, and I'm going to do a little bit of a shameless plug here, but if you were to look at the new technology coming along, the MEMS-based technology, how is that assisting within research just like yours here?
Well, basically, first of all, it will be faster.
Okay.
You will have a certain value of electric field. Yeah, and you will have a high beta tilt possibility with that. So these three very important things, at least for me. Okay, I'm gonna show you some results, and here you can see the rhombohedral BZT-0.3 BZT composition. At the initial states, you can see a lot of lamella domains, and in such needle shape, which are very typical for rhombohedral type of material. When we increase an electric field up to 5 kV per centimeter, direction of the field you can see here, transformation from the multiple domain state to the single domain state occurs. And it's you can see that whole grain becomes one single domain. Okay, so now I would like to show you a video. Here you can see another representative grain of the same composition. And the video shows three neighbors grain basically, and prior to applying an electric field, we see a domain contrast within the grains. With increasing electric field, we can see changes in domain contrast, which indicates a switching of ferroelectric domains. With further increase of electric field, it will happen at approximately 4 kV per centimeter. Our transformation to the multiple, from the multiple to single domain state will occur. So you see that now that whole grain became a large single domain basically.
So why are domains critical for ferroelectrics?
Well, yeah, so what is actually ferroelectrics domains? Ferroelectrics domains is regions within the grains, like here, which exhibit a uniform polarization. And piezoelectric ceramics are characterized by very well defined domain walls, which are critical for dielectric, piezoelectric, and ferroelectric properties of these materials. And since the external electric field, like here, induces domain wall motion and domain switching, basically it's very, very critical to perform such kind of in situ biasing experiments in that material to compare it with properties. Okay. So let's come back for this video. Basically, with reducing an electric field, we see that this single to multi-domain transformation is occurs. So we have a completely reversible transformation in that case. And at zero field, we have a multiple domain contrast again. On changing polarity will lead basically to the same result as another direction. So what did we have? We saw that electric field induced transformation from multi to single domain state, and this actually occurred at the moderate Poling fields. And this transformation is found to be reversible since multidomain contrast reappears on field removal basically. For the orthorhombic BZT 0.45 BZT composition, grain orientated along 011 zone axis was chosen for this kind of experiment, and you can see that at zero field domain orientated in 111 direction are visible. However, within some domains you can see a further contrast, which we define as nanodomains. With increasing the Poling field up to 2.1 kV per centimeter, we see that this nanodomains basically grows. And at further increase, we appears again the single domain state. So what is actually interesting, if you will compare this two diffraction patterns, there is no basically difference. There is no any reflection splitting on that.
So on that point, actually, why was there no spot splitting in the diffraction patterns?
Yeah, this is actually the right question. So, because we should see something, there should be this unit cell distortions, and therefore should be visible some spot splitting in diffraction pattern, of course. So, we attribute this fact to the very, very small distortions, which results in very, very thin split, this peak splitting. Which cannot be detected in the diffraction patterns due to the resolution limit. So actually we performed the theoretical analysis of reflection splitting for rhombohedral and tetragonal ferroelectric domains. You can see it in this paper, and it was performed by Roland Schildholz. And actually what he obtained, it was that the highest amount of splitting was observed in tetragonal domains. However, the splitting was still so small that it was impossible basically to detect it in diffraction patterns. Okay, let's have a look on polymorphic phase transition composition. It's BZT 0.52 BZT. And at the initial state, the virgin state, we can see this hierarchical domain structure. The grain orientated along 110 zone axis, you can see it here. Increasing electric field up to 1.6 kV per centimeter already led to formation of the single domain states. However, that's interestingly that further increase of electric fields leads to the multiple domain formation again. On field removal and at zero field, we didn't get any single domain state in between of these two basically. And on changing polarity, it was very, very difficult to achieve that again. Actually, it was achieved only at 6.5 kV per centimeter. However, already after a few seconds, we saw a huge amount of domains basically. So this state was not stable at all.
So why does the transformation to a multiple domain state occur again at higher fields?
Yeah, this so basically we attribute it to the very high strain between neighbor grains. So what I mean here, so that high Poling fields under high Poling fields, each grain represents a single domain, like here, for example. With respect to this electric field, preferred alignment of the polarization vector cannot be completely achieved within this grain and all neighbor grains for like polycrystalline samples. And therefore, strain incompatibility between these grains and another surrounding play a very crucial and important role in this thing, and that's why basically we have transformation to this multiple domain state. Okay, let's have a look on the trigonal composition. For the BZT-xBCT, we performed the same kind of experiment. The grain was imaged along 112 zone axis, and at zero field we saw such lamellar domains. Increasing the field up to 8.6 kV per centimeter induce a appearance of nanodomain state. However, in this case, we didn't got our single domain state even at 12 kV per centimeter. On field removal, we saw a nanodomain state as well at zero field, and after changing polarity, basically, no crucial changes appeared up to 8.6 kV per centimeter. So, however, actually we got our single domain state, but it happened at 20 kV per centimeter, which is very huge.
So why does the single domain state occur at much higher Poling field for this composition?
So basically this agrees with the high accuracy fields measured when approaching a tetragonal symmetry. Therefore, higher fields are required to achieve a proper polling of BZT-xBCT, which locates very, very deep in the tetragonal region of phase diagram. Okay, based on our results, we propose such a kind of scheme of domain evolution. So here you can see a grain with it's one grain with the domains. During applying an electric field, we have a transformation from multiple to single domain state. In some material, it happens that the nanodomain state occurs in between. This situation is completely reversible. So we, on the reducing the field, we see a multiple domain state again. However, if you will increase field after that situation, so basically here, again this multiple domain contrast will appear, and after that we already will have only switching between two different multiple domain states, basically A and B. Okay, so finally I just would like to summarize what I was talking about today. First of all, we observe the transformation from a multi to single domain state with increasing the Poling field. We saw the appearance of nanodomain state at the moderate Poling fields. We saw that this single domain state is not stable against higher fields and transform again to our multiple domain state. So just in conclusion, what can we tell? Basically, domain wall motion during electrical polling can be a sign of high extrinsic contribution to the piezoelectric properties in our material. And stress are suggested to determine the domain configuration evolution under the field.
So can you tell me a little bit about, I guess, the future of this research and where it's heading with new technology, for example?
So first of all, I would tell you what is, I think, very important for that kind of materials to do. So first of all, extremely interesting would be to perform electric field experiments at higher temperature, because the influence of the temperature for this for temperature-induced phase transition during polling process on this material are not really studied and is not clear, basically. And in order to optimize its application, such studies are kind of required, of course. So, and I believe for that reason, one possibility would be to use MEMS-based holders, for example, where you can apply voltage and at the same time increase temperature. So yeah, this would be interesting, I believe.
Okay. So just to finish up, do you want to just tell us a little bit about what you're now doing and what you'll be doing in the next, I guess, time with DENSsolutions?
Of course. So I'm a product marketing engineer, and at the moment I'm responsible for two systems. It is Wildfire, which is already on the market and widely used all over the world. And second system is Lightning. It is heating, which enable heating and biasing at the same time. So as I had quite a bit of experience in biasing, and as well I had a huge experience in heating, I believe that I can really help in development in I don't know, in some application spaces so I plan to work closely to the customers to kind of help their research from my point of view, let's say, from my experience. So that's basically it.
Great. So as part of Nanotalks, we want to make sure that we promote the leaders in the industry and especially the contacts directly to you. So do you have any shout outs or recommendations that people can look into of leading researchers out in the field?
Well, first of all, of course, I would like to promote my previous group where I've been for 3 years. It's a group of Professor Kliebe in Technical University of Darmstadt. They have a huge experience not only in situ TEM techniques, but also in this kind of materials, which I was talking today. Another group is a group of Professor Rudel. They're also from Technical University Darmstadt. They have very huge range of huge experience in studying different ferroelectric materials. If you're interested in situ TEM experiments, I think the main name would be Professor Tan from Iowa State University. I believe he was one of the first people who started this in situ biasing experiments in ferroelectric materials, and of course he has a lot of knowledge and a lot of experience in that things as well. Okay, that's basically it. Thank you very much for your attention, and if you have any kind of questions, you can contact me via this email address, basically. Thanks a lot.
Well, thank you so much, Marina, and thank you must be going out to everyone at the Technical University of Darmstadt for obviously their involvement and contribution, and we'll be having all these details up on the website under the Nanotalks page after this Nanotalk. So if you have any questions, do send them through to Marina, or we'll have the contact details for the other members in the group as well, and we look forward to seeing you at the next Nanotalks. Thanks, bye.
Thank you. Ciao.
So thanks for watching episode 2 of Nanotalks, and Nanotalks made possible by DENSsolutions. DENSsolutions, your one-stop shop and complete solution for all your in situ needs, offering the Wildfire Heating Series, Lightning Biasing and Heating Series, Climate Gas and Heating Series, and Ocean Liquid Series. And if you would like to come on to Nanotalks or know someone else doing some really interesting in situ research, definitely drop us an email on nanotalks@denssolutions.com or visit us on our website on www.denssolutions.com/nanotalks. And we hope to see you next time.